This lecture is on the video coding, and in this lecture we are going to discuss about the basic building blocks and how to exploit the temporal redundancy. Now, so far we have seen the image compression standards. Now, a still image, as you have already seen, that a still image does not have temporal information, it has got only the spatial information, and once for all we have to send a frame of image, okay, and that is it. So, that should be encoded by the encoder at the transmitter end, and at the receiver end it should be decoded and the receiver can reconstruct the image. Okay. Whereas, in the case of video, we have a continuous stream of images which will be available, okay, from a video camera or some stored video medium. Now, what are the different applications? So, the applications of video communications, okay, one can broadly categorize into two major application areas. One is what is called as the conversational video, and under this conversational video category we have video telephony, video conferencing, video telephony and video conferencing. This could be through wired or wireless medium. And the other application, major application domain is the streaming video. Like this video which you are watching, okay, through the net, and you are able to download it into your own terminal and able to see as a video on demand. This is a streaming video application. Okay. So, this is a so video on demand is one of the major application of streaming video, where some recorded video is already there, recorded video in digital medium, in the computer or in the digital medium it is there, and you can just get that video stream and play it into your system. Okay. That is what you are having as a streaming video. Means streaming video means that as the video stream is being sent, okay, you are also simultaneously watching. You need not have to wait until the complete video is downloaded. Even if a part of it has been sent from the encoder to the receiver, once you start receiving, once you are in a position to play some frames, okay, the playing can commence while the subsequent video stream would be sent from the encoder to the decoder. So, that is the streaming application. So, one has got video on demand, HD TV applications, okay, then image or video database services, etc. Okay, those are the streaming video applications. So, these are the two major areas, conversational and streaming video, which will be addressed in the video coding. Now, what is the basic difference that we are going to have between the still image coding or compression and video coding. The first and foremost difference is that in the case of video, we are having the temporal aspect of the signal. The signal is not only varying in space, but the signal is also varying in time. Okay. And there is a great deal of similarity between the signal that varies in time, because what is being done is that the video is captured at a particular frame rate. Okay. Let us say that the frame rate of the video is 30 frames per second. So, 30 frames per second means within 1 second we are capturing 30 different frames at a time of 33 milliseconds apart. We are just sampling each and every frame, and if we are comparing successive frames, then we will be finding that within the successive frames there will be a great deal of similarity. Okay. Because the physical movement that can take place within a time span of 30 milliseconds is highly limited. Okay. I mean, even this video what you are watching here, how much of movement can you see from one frame to the next? Okay. If you are really analyzing, you will be finding that the background is stationary. Okay. It is only that when a person is talking, like here I am talking, you will be finding that there is a lip movement, there is eye movement. Okay. Sometimes shoulder movements are there. Okay. A limited degree of movement you will be observing. So, that there is a great deal of temporal redundancy that is present, and this temporal redundancy also can be exploited in addition to the spatial redundancy. Now, in the case of still image, we could see that only the spatial redundancy could be exploited. And how did we exploit that? We had transformed the still image from its original spatial domain into a transform domain space, like the discrete cosine transform or the discrete wavelet transform. Okay. And then we worked with those transformed coefficients and encoded and sent the bits, sent the bit stream. So, we had essentially used the transform domain approach, although there are alternatives to the transform domain approach also, like just as in the case of the speech, we could use the differential pulse code modulation scheme, adaptive differential pulse code modulation schemes, etc. Images also can very well make use of that. DPCM could be used for images also. And what is DPCM or ADPCM, whatever you can talk of? It is basically a predictive coding technique, but that prediction has to be a spatial prediction. In the case of still image, one has to predict a pixel by observing the values of the past transmitted pixels. In the case of speech, what is the mechanism of prediction? We had temporal prediction, that the time domain samples which are arriving, okay, based on the past time domain samples, we are predicting what the next sample is going to be. So, it is a temporal prediction, whereas in still image it has to be a spatial prediction. But now, in the case of video, we are having both variations with respect to space and variation with respect to time. Now, as far as the spatial redundancy is concerned, it is a proven fact that transform domain technique can exploit the spatial redundancies much better as compared to predictive encoding for spatial domain. But again, looking at what we had learnt in the speech, we had seen that for time domain redundancy exploitation, predictive coding is also a very good and effective technique. So, why not have a combination of these two techniques? Means, as far as the removal of the spatial redundancy is concerned, adopt a spatial domain technique, and as far as removal of time domain is concerned, adopt a adopt a spatial domain adopt a transform domain technique, whereas in the case of removal of temporal redundancy, there you adopt a predictive coding technique. So, what essentially evolves is a hybrid coding technique. So, it leads to a hybrid video codec, okay, hybrid video codec, where the first and foremost thing what is done is that the temporal redundancy is exploited by predictive coding. Now, how would you perform a predictive coding? If you are accepting the video sequence, okay, then you are also having successive frames are coming, and if you have a storage, if you have a memory to store the past frame, then you can make use of the past frame to predict what the present frame is going to be, okay. Because as I had told you that between successive frames there may not be much of change in the information. So, the past frame can very well predict what the next frame is going to be, and then if you and then but the prediction is not going to be exact definitely, because there will be some changes, even though there are parts where there will be no change, like the background, the stationary background especially, but there will be areas where there will be changes. So, if you are predicting only based on the past frame, okay, you are going to have some prediction error. Now, that prediction error, okay, would have some kind of a spatial similarity, means the prediction error that we have, I mean between successive pixels, okay, in space, we will be finding that there is not much of change in the prediction error signal, and that can be very well exploited by a transform domain technique. So, spatial redundancy, I can tell it like this, that spatial redundancy of prediction error signal, the temporal prediction error signals, that can be that is exploited by transform domain coding. So, in the video encoding process that we are going to utilize, we are going to have a combination of predictive coding for temporal redundancy and transform domain technique, transform domain coding for residual spatial redundancy. We can call it as a residue. Why residue? Because it is the temporal prediction error that we are encoding through the transform domain. So, it is a combination of predictive and transform domain coding, and that is why this is called as the hybrid video codec. So, in a typical hybrid video codec, what we are going to have is like this, that here we are having input video, okay. Here we are going to have a block where the input video will be subtracted from the predicted video. Now, how that predicted video is generated, that part we will be seeing, but at least one thing is very clear, that if this is with a plus sign and this is with a minus sign, in that case what we get here is the prediction error, okay. And as we said, that prediction error or the residual signal, and the residual signal has to be transform coded. So, there will be a transform block, okay. that transform block could be DCT or a DWT. Okay. Let us say DCT, because again DCT is the coding technique that has been used in all the popular video coding standards that have evolved through date. Okay. I will be mentioning about the video coding standards very shortly, but okay, DCT is just a specific case of the transform that one can use on the residual signal, and this DCT has to be followed up by a quantizer. These blocks we also had, remember, in the JPEG encoding scheme. There it was the original image which was DCT encoded and then quantized. In this case it is the residual video signal. So, the quantized signal then could be coded through the entropy coding technique, just like the way we did for the still image. So, this is an entropy encoder, and the entropy encoder will generate the final bit stream. Now, this is the forward path of the encoder, which looks very clear. So, that means to say that what this bit stream is encoding is not the signal, but it is encoding the residual signal, the prediction error signal. Okay. So, somehow that prediction error should be, should be that information, and how to predict that information should be conveyed from the encoder to the decoder also. So, that decoder can in turn generate what the encoder what the original video was. Of course, exact reconstruction will not be possible because we have a quantizer present here, quantizer will be a lossy. So, exact reconstruction will not be there, but you can start thinking about what you will be finding in the decoder, because decoder will have a reversal of this process. So, what will a decoder block diagram look like? The bit stream will be received, the bit stream will go through an entropy decoder, then there is a quantizer in the encoder. So, we have to have a dequantizer. What is a dequantizer? In the process of quantization, what are we doing? We are dividing the coefficient value by some quantization matrix elements. In this case, this already quantized values have to be multiplied by the quantization matrix element. So, there will be a dequantizer. And here we had the DCT or the direct transform. Okay. In this case, we are going to have an inverse transform. So, we are going to have the inverse transform, or in this specific case IDCT, inverse DCT we have to do. But here what do we get? Here we are going to get only the error signal, but the error signal is not the one that we want to show onto the screen, okay, onto the display. In the display we want to show the proper video, not the residual signal. But how do we obtain the error signal? It is input minus predicted, that is error. So, if we add the predicted to the error, what do we get? We get input, not the exact input, because even this. So, if we call this signal as S n1 comma n2 comma k. So, I have now introduced. So, S n1 n2 I was so long indicating as the pixel intensity at the position n1 n2. Now, I am denoting the intensity as S of n1 n2 k. So, there are 3 variables that have come in, and what is the third variable? The third variable is the time. Okay. So, it is a frame number. So, this is also an integer. So, n1, n2, k, all of these are in integer. So, that essentially I can say that this n1, n2, k, okay, this belongs to a 3 dimensional integer space, okay, lambda cube. So, what it means to say is that this is the input video signal, and the predicted video signal also will be we can denote as S cap of n1 n2 k, right. So, that the error we will be denoting as E n1 n2 k, right. Now, here what we are going to get at the IDCT output, we want to get E n1 n2 k, but we will not get exactly E n1 n2 k, we will get E dot n1 n2 k. Why? Because of this quantizer at the encoder. So, we have got E dot n1 n2 k, and if we have a block where we add or sum up E dot n1 n2 k with the predicted video, that is S cap n1 n2 k, what are we going to get? We are going to get the reconstructed video, or we will write it as S dot n1 n2 k. So, this will be what we are going to expect at the decoder, and this is what we are expecting at the encoder, but I have not completed my job yet. What I have shown is only a part of the encoder and a part of the decoder, only looking at the forward path, but I have left this issue open, that how to generate the predicted video. The only fact that I made a brief mention is that the predicted video should be generated from the past video frames. So, I must be having the signal corresponding to S n1 n2 k minus 1, or in general k minus L, where L is a number which is greater than 0. So, any frame which is S n1 n2 k minus L with L greater than 0 basically refers to the past frames, okay. And if I get some of the past frames, then I should be able to predict this one. So, how to generate the past frame? Again, here I have got only the error signal, okay, and that too at this point it is transformed already. Now, you can well argue that, well, generation of the predicted video is not a problem. You take the input video you take directly, you store it into some memory, okay. You get the past video frame, okay, and you compare the past video frame with the input video, okay, find out that how much of displacements every block of the image has undergone, okay, and then you can generate the predicted video from here. Why do you have to derive the signal from here? Because after all, if you have to derive, you have to derive from this point, from the quantizer. Well, encoder can do that, but can a decoder do that? No, because the decoder does not have this input video information anymore. What the decoder is going to have is only this encoded information, okay. After the entropy, so by a process of entropy decoding, because entropy encoding is a lossless process, at the end of entropy decoding, the decoder gets back exactly what you have over here, the decoder will get back at its end. So, the best point should be the, so the philosophy of generating the predicted video should be the way decoder is going to predict, okay, in the same manner the encoder is also going to predict. so that whatever error encoder has got, okay, that error's residues can be encoded and sent into the bit stream, okay. And the decoder will generate that in a very similar manner, because the decoder is also having presence of this signal, but the decoder is not having the presence of this signal. So, because of this reason we have to tap and derive the stored video, okay, from this part. So, how do we do that? So, here we have to do a mimicking of the decoder part. What did we do at the decoder? We had put forward an entropy decoder, dequantizer, IDCT and generated E dot. In this case, what we have to do is, we do not have to use entropy decoder, because this is before the entropy encoding where we are tapping. So, what should be the block that we are going to have over here? Dequantizer. So, here we keep a dequantizer. The next block should be an IDCT, right, and output of IDCT would give me E dot N1 N2 K, right. Now, if I have a predicted video, I still do not know how have I generated predicted video, but if I have a predicted video, in that case what I should do is that I should add up this is escape N1 N2 K, that we should add up, and what do we obtain? We obtain S dot N1 N2 K, exactly what decoder also is able to obtain, provided there is a good mechanism of getting the predicted video. So, here we will be getting S dot N1 N2 K, and now we can have a frame store. So, this is a frame storage. So, at the output of the frame store, what we get? We get S dot N1 N2 K minus 1. If it is a storage of only one frame, then we have S dot N1 N2 K minus 1 available at the output of the frame store. Now, you have S N1 N2 K, the incoming video over here, and then you are having the S dot N1 N2 K minus 1, the past frame. You compare the present frame with the past frame, okay, and using that, what you can get? You can find out that there will be some regions where there will be no change in the intensity, and there will be some regions where there will be some change in the intensity because of the movements. Basically, it is something like this, that you have a frame, okay, and supposing you have got an object which is at this position, say the centroid of the object is some point N1 N2. So, this is at the frame K now, or this is at the frame K minus 1, and at frame K what will happen is that this same object, okay, moves, okay. The very simplistic assumption is that it undergoes a translational movement. That is a simplistic assumption. If it does a translational movement, okay, in that case what we are going to have? Translational movement is going to have an x component and a y component, or since we assume the directions as N1 and N2, the translational movement will be having one component along N1 direction, one component along N2 direction, so that the translational movement can be specified as a 2 element vector, right. So, the translational movement can be specified by a 2 element vector, and we are going to call that as 2 element displacement vector, okay. And we can denote it as D vector, where D vector's elements are D1, D2 transpose, right. So, this is so D1 is the displacement along the n1 direction, D2 is the displacement along n2 direction, and this is the displacement vector, or also known as the motion vector. Basically, the motion vector refers to the same displacement vector only. So, now if we compare this k1 frame with k, then what we will be observing is that there will be some regions where the displacement is 0, and there will be some moving objects, okay, where the displacements will be non-zero. So, we have to estimate those displacements. How we can do? By matching, by doing a proper matching of the past frame with the present frame. And in the process of matching, what we will be getting is that, I mean, the ideal situation would be that if we can generate a pixel to pixel matching, but that will be highly time consuming, okay, and not very practicable, simply because just by comparing a pixel's intensity with another frame's pixel intensity, you cannot be sure that this pixel corresponds to that pixel, because by fluke or by accident, I mean, the two pixels can have the same intensity, but only if there is a matching not only with the pixel, but along with the pixel its neighborhoods also match with the pixel and its neighborhood in the other image, then only we can be confident of saying that this is a proper matching. So, it is not only just a pixel matching, but a neighborhood matching. How to specify the neighborhood? Well, one can define a small region, but instead of specifying a region arbitrarily, then again the issues will come that how to specify the region. Do we take circular regions? Do you take rectangular regions? Do you take any arbitrary regions? Well, the simplest of that could be a square or a rectangular region, and because we are already familiar with the partitioning of an image into non-overlapping blocks, we did that in the DCT or the transform domain coding. We were subdividing the image into a set of non-overlapping blocks. Okay. Applying a very similar philosophy, we can divide the frame into a set of non-overlapping blocks, and for each block we can measure that how much of displacement it has undergone. So, the process of finding out this displacement, it is basically a search technique, okay, and this technique is popularly known as motion estimation. So, this aspect was completely missing in the case of still image compression. Still image did not have anything called motion estimation, but in this case, in the case of video, we are going to have a motion estimation process, so that the displacements undergone by every block can be measured with respect to its past frame. So, what we are going to have is that this frame store output has to be compared with the input video, okay, and we are going to call that block as motion estimator. Okay. And what this motion estimator is going to generate? Motion estimator will find out the motion vectors for every block. It will be able to generate the motion vectors for every block, and this motion vector Why is it useful to us? If I know that how much of motion is undergone by which block, then I can fictitiously apply that motion into my stored frame, okay, and then generate the predicted frame. If I know that okay, this is expected to move this much, so I can generate a fictitious displacement, okay, and I can predict a frame. So, what we do is that there will be a motion prediction block, and the motion prediction block will work on the stored frame by applying the motion vectors. I call it as MV, and by applying the frame store onto the motion prediction, okay, we can generate the predicted video. So, this is how we complete the path. Now, this is in the encoder part, and if you look at this, no, not this, sorry, take out this part and let me draw it in a different color. So, the part that I have shown within this red dotted border can also be used in the decoder. Am I right? There is no difficulty. Only this motion estimation I cannot do, because motion estimation requires input video and I do not have input video at the decoder. For motion prediction, what do we require? We require the use of the stored frame and motion vector. So, that means to say that the decoder must get the information about this motion vector. So, this motion vector also has to be sent into the bit stream. So, we must derive a tapping from here. Okay. So, just to avoid clumsiness in the drawing, I use a different color. So, this is the motion vector which will go into this place, where the motion vector also will be having some similarities between themselves. That means to say that motion vector of one block to the motion vector of the next blocks or in the neighboring blocks are going to have some kind of similarity. So, you can exploit that in the entropy encoding process. So, the motion vectors can go through the entropy encoded scheme and go into the bit stream. So, this bit stream, what you are containing, what we are sending is not only the encoded error bit stream, but also the encoded motion vector bit stream. So, at the decoder block diagram, we this bit stream can have the two components, one is the motion vector and the other is the signal. Now, as far as the signal is concerned, so after the entropy decoding, okay, we make a bifurcation. The signal part goes to the dequantizer and IDCT to derive this E dot n1 into k, and the motion vector that can be used, okay, in this motion vector, motion prediction and frame store. So, I can in fact draw it as a single block. So, motion prediction plus frame store. Now, what does frame store require? Frame store requires S dot n1 into k, right. In the encoder it required S dot n1 into k. Decoder also we have got S dot n1 into k available from here. So, S dot n1 into k could be fed to the frame store block. The motion vector is coming over here. So, the motion prediction plus frame store would be done from here, and this is generating the predicted video S cap in 1 into k, just like the way it is done even here also. I mean, all that we have done is that this frame store and motion prediction we have combined into one single block, but the output of the motion prediction block is the predicted video S cap in 1 into k. So, even here also it will be S cap in 1 into k. So, this is the complete decoder. So, this is the basic philosophy behind the hybrid video coding. Anybody having any doubts at this stage? Okay. Before we proceed further into this, yes.
The audio part, which forms part of the video, this also follow the same, or it is interact on the video signal as a separate process separately and then send it?
Well, the question that you are asking basically goes back to the issue of a transmission of both audio and video in a synchronized form. So, that is a different problem altogether, which is addressed as a part of the multimedia communication. So, I am not addressing that issue in this course, okay. But it is a very intricate issue that yes, the audio and video bit streams which are independently generated, they have to be properly synchronized and then multiplexed into the bit stream, okay. And there are techniques, there are standards for that. So, one has to follow those to do this, okay. So, the idea that I am pursuing here is only pertaining to the video coding. Now, there are a few issues that needs discussion at this stage, okay. Now, what are the new elements that we learned from this block diagram? One major aspect that we have learned is that a very efficient motion estimation technique has to be carried out at the encoder, right. Why efficient? Because you see, as we had seen just by reference to an example like this, that we have to determine the motion vectors for every individual blocks. Now, if I subdivide this image into non-overlapping blocks like this, let us say of 8 by 8 size, okay. Supposing I subdivide the image into 8 by 8 non-overlapping blocks like this, and then I estimate the motion vector for each individual block, just try to see the computational intricacies which are involved in that. To find out the motion vector, we have to do a matching, and we do not know a priori that whether this particular block of pixels have moved to the left or to the right or to the top or to the bottom. It can move in any of these directions. I mean, assuming a translational movement, it has got 2 degrees of freedom. It can move in positive x, negative x, positive y, negative y. Now, so that means to say that one has to have a search, and the search is complicated in the sense that whenever we are matching one block with a block that is present in the past frame, the past frame is actually used as a reference. In this case, in the block diagram, what we have essentially done is that the image that we obtain from the frame store, that is the past reference frame, whereas the input video is being called as the candidate frame, and this is the past frame. Candidate frame is one which we are going to encode, and past frame is what we are using as a reference. So, the two terms that we use is candidate and the reference. Now, what we have to do while searching is that we have to search for a within a range, and then when we have to search for every position, we have to find out that what is the similarity in this block of pixels with that in the reference frame. Candidate block to be compared with a reference block now. And if the block size is 8 by 8, then we have to compare the values for 64 pixels, 8 by 8, that is 64 pixels, and that we have to do for only one search position, but there will be several search position. If I specify a search range, that okay, I mean any unlimited search range one need not have to use, because as I told that the movement between the consecutive frames are going to be quite restricted. So, that is why we did not have to search over a very long search range or very large search range. We can restrict the search range, but even within the restricted search range also we have to do lot of searchings. So, there will be good computational issues that will be involved, and there are some techniques in order to have very efficient search technique computation. Although the optimal search technique is always the one which is carrying out an exhaustive search, or what is known as the full search block motion. So, this way of estimating the motion by subdividing the pixel into blocks like this, it is called as the block matching technique or block motion estimation, technique, okay, whereby we are subdividing the image into small blocks and estimating its motion. And whenever we are searching over the entire search range and having estimating the motion, we call it as full search block motion, or in short form it is called as FSBM. Now, FSBM guarantees that you will be able to find out the optimal position at which the search is the best. Now, how to quantify that search, or rather how to measure the quality of that search, that I will cover in the next lecture. Okay. And then we will also talk about some efficient techniques for that, which have been used in some of the popular standards, and we will also talk about some of the popular video compression standards. Okay. Thank you.